Our universe is held together by a ghost. Galaxies spin so fast they should tear themselves apart, yet they do not. Vast clusters of galaxies move with a gravitational pull that comes from seemingly nothing. This invisible anchor, this cosmic phantom, is what we call dark matter. It makes up over 80% of all the matter in existence, and we have never seen it directly. This is the story of the greatest treasure hunt in scientific history. By the end, you will understand the 20 monumental experiments searching for this ghost and the profound reasons it continues to evade us. You will see how the most brilliant minds on Earth have built machines of stunning sensitivity, only to be met with silence. What does this cosmic silence mean? And what happens if the ghost is something we have not even dreamed of? This journey reveals a beautiful contradiction: the relentless ingenuity of humanity facing the stubborn secrecy of the cosmos. What does it feel like to chase a shadow that shapes the universe? The first clue came not from a machine, but from the silent motion of distant suns. In the 1970s, astronomer Vera Rubin pointed her telescope toward the Andromeda Galaxy, our closest cosmic neighbor. She meticulously tracked the speeds of stars swirling within its vast spiral arms, expecting a simple cosmic rule to hold true. According to the laws of gravity, stars farther from a galaxy's bright center should move slower, just as planets in our own solar system orbit more sedately the farther they are from the sun. But the data told a different story entirely. Stars on the outer edges of the galaxy were racing at nearly the same high speeds as those near the core. It was as if every star, regardless of its position, was caught in a powerful, invisible current. The visible mass of stars and gas simply could not generate enough gravity to hold these speeding suns in place. They should have been flung out into the blackness of intergalactic space, yet there they were, held by an unseen hand. This discovery, the galactic rotation curve anomaly, was a quiet revolution. It provided the first robust, undeniable evidence that galaxies are embedded within vast, massive halos of something that does not shine. Vera Rubin did not invent dark matter. She revealed its signature in the motion of the heavens. This single observation transformed a theoretical curiosity into a concrete cosmic problem. It was the first great experiment conducted by the universe itself, and its results demanded an answer. The hunt for the ghost was now a scientific imperative. That unseen hand leaves fingerprints across the cosmos, not just in the motion of stars, but in the very path of light itself. This is the realm of gravitational lensing, our second great window into the ghost. It relies on a prediction from Einstein's theory of general relativity that massive objects warp the fabric of space and time around them. Think of placing a heavy bowling ball on a taut, stretched rubber sheet. The sheet dips. Now roll a marble past the bowling ball, and its path will curve, following the dip in the sheet. In the universe, the bowling ball is a concentration of mass, like a cluster of galaxies filled with dark matter. The marble is a beam of light from a galaxy billions of light years behind it. As that distant light travels toward us, it passes through the warped space around the foreground cluster. The light does not travel in a straight line, it bends. From our vantage point, the image of that background galaxy is distorted. It might appear as a stretched arc, a smeared ring, or even multiple copies of the same galaxy arrayed around the central cluster like a cosmic mirage. This is gravitational lensing in action. The crucial point is this: the degree of bending depends entirely on the total mass causing the warp. The more mass, the stronger the lens. Since the visible galaxies in the cluster account for only a tiny fraction of the needed mass, the dramatic lensing effects we see are caused overwhelmingly by the dark matter halo. Experiments like those conducted with the Hubble Space Telescope use this phenomenon as a celestial scale. By meticulously measuring the distortions of millions of faint, distant galaxies, astronomers can literally map the distribution of the invisible mass that is bending their light. They can trace the outlines of dark matter filaments that connect galaxy clusters, weaving the cosmic web. These maps are not pictures of dark matter, they are pictures of its profound gravitational shadow. The upcoming Nancy Grace Roman Space Telescope will take this survey to a staggering new level. With a field of view 100 times larger than Hubble's, it will perform a vast, systematic census of these subtle distortions across an immense swath of the sky. The goal is to create the most detailed, three-dimensional mass map of the universe ever made, charting the growth of the dark matter web over cosmic time. This is not looking for a particle in a lab. It is using the universe itself as a giant lensing experiment, revealing the ghost's architecture on the grandest possible stage. But how do you catch a ghost on Earth? You must think like one. If dark matter is a particle, it must be streaming through everything around us right now, passing through our planet, our homes, our very bodies with almost no trace. To detect it, you need to build a trap of unimaginable quiet and patience. This led to the third great experimental approach, direct detection, and its most famous quarry, the WIMP. The name itself is a perfect summary, a weakly interacting massive particle. It is the leading candidate, a hypothetical particle with enough mass to provide the gravitational glue, yet so shy it interacts with ordinary matter only through the feeblest of nudges, perhaps just the weak nuclear force and gravity. The strategy is straightforward in theory. Build a pristine target of atoms and wait for a WIMP to bump into one of their nuclei. That tiny collision, a microscopic recoil, would deposit a minuscule amount of energy in the detector. In practice, it is one of the hardest challenges in modern science. You are listening for a single, faint whisper in a universe of constant shouting. Every natural source is noise, cosmic rays from space, trace radioactivity from the very rocks of the Earth, even the faint decay of atoms in the detector materials themselves. To hear the ghost's whisper, you must silence the world. This is why these experiments live in the deepest underground laboratories on the planet. Places like the Gran Sasso Mountain in Italy or the Homestake Mine in South Dakota. Miles of solid rock act as a shield, blocking most cosmic rays. The detectors themselves are marvels of purity, built from materials selected and processed for years to eliminate radioactive contaminants. They are often cooled to temperatures near absolute zero, becoming cryogenic sensors of incredible sensitivity, able to feel the faintest warmth from a single atomic jolt. For decades, this has been the front line of the hunt, and here a tantalizing mystery emerged. One of the pioneering experiments, called DAMA/LIBRA, located deep under Gran Sasso, has reported a strange signal for over 2 decades. It sees a rhythmic flicker in its detector counts that rises and falls with a precise 1-year cycle. The team suggests this could be the signature of dark matter. As Earth orbits the Sun, it moves through the galactic halo of dark matter. In June, our planet is plowing headfirst into this cosmic wind, perhaps creating a higher rate of collisions. In December, we are moving with the wind, resulting in a lower rate. This annual modulation is a predicted hallmark of a galactic dark matter wind. Yet, no other major experiment has been able to confirm this signal using different target materials and techniques. The DAMA result remains a persistent, controversial enigma, a siren song from the deep that keeps the community both skeptical and utterly captivated. Is it the first faint touch of the ghost, or is it an elaborate echo of something much more ordinary? The quest to find out has spawned a generation of ever more sensitive detectors, each one a deeper listen into the cosmic silence. Deep underground, in caverns of profound stillness, the most sensitive ears on the planet are listening. They are not microphones, but vats of liquid xenon, the heart of the fourth great experimental front. These are the time projection chambers, and they represent the pinnacle of our search for the ghost's direct touch. Think of a giant, three-dimensional camera built to capture not light, but the faintest splash of energy from a single atomic nucleus. At their core is a crucial choice of material, xenon. This noble gas, when purified to an almost impossible degree and cooled to -100 degrees Celsius, becomes a dense, ultra-pure liquid. It is an ideal target because xenon atoms are heavy, making them a bigger sail to catch the gentle breeze of a passing WIMP. Furthermore, xenon is exceptionally good at producing two distinct signals when its atoms are disturbed, a quick flash of light and a delayed pulse of electrons. This dual signature is the experiment's genius. Here is how it works. The experiment, like the Large Underground Xenon Experiment, or LUX, is a stainless steel tank filled with several tons of this liquid xenon. At the top and bottom of the tank are arrays of exquisitely sensitive light sensors. If a particle, any particle, interacts in the xenon, it will produce a tiny flash of light called the S1 signal. The sensors immediately record this, but if the interaction was with a xenon nucleus like the hoped-for WIMP bump, it will also knock electrons loose. An electric field stretched across the entire volume of the tank draws these freed electrons upward. When they reach a thin layer of xenon gas at the top of the detector, they produce a second distinct flash of light, the S2 signal. The crucial detail is this: the time between the S1 and S2 signal tells you precisely how deep in the tank the interaction occurred. By combining the timing and the brightness of both signals, scientists can create a three-dimensional map of every single event inside the detector. This allows them to perform a powerful act of discrimination. Background events like gamma rays or electrons tend to interact more with the outer electron cloud of the xenon atom, producing a different pattern of light. The hoped-for nuclear recoil from a WIMP would have a very specific fingerprint. The entire apparatus is designed to find that one unique signature amidst a sea of ordinary noise. The scale of these endeavors is breathtaking. The XENONnT experiment in Italy uses over 8 tons of liquid xenon. The LZ or LUX-ZEPLIN experiment in South Dakota uses 10 tons. These are not just detectors, they are the most radioactively quiet environments ever created by human hands. Every component, from the titanium holding the xenon to the cables carrying the signals, is selected, cleaned, and tested for years to eliminate even the faintest whisper of natural radioactivity. They represent a collective investment of decades and hundreds of millions of dollars, a testament to the global priority of this search. And so far, the result is a profound and growing silence. These magnificent machines have seen nothing that can be definitively called a dark matter particle. They have not found the WIMP. This null result is not a failure, it is a powerful form of discovery. Each experiment, by seeing nothing, rules out vast territories of possibility. They tell us that if the WIMP exists, it must be even more weakly interacting, or perhaps slightly heavier or lighter than we once thought. They are meticulously carving away the map of what dark matter is not, forcing the ghost into an ever tighter corner of theoretical space. The silence from these tons of xenon is a message, one that is reshaping the entire hunt. Yet the silence from the xenon chambers is not the only story being written in the dark. Deep underground, a different element is telling its own tale. This is the world of liquid argon, a parallel and powerful strategy in the direct detection hunt. While xenon is the heavy, quiet sentinel, argon is the swift, discerning analyst. It offers a different set of clues for identifying the ghost's touch. Experiments like DarkSide in Italy and Deep in Canada have built vast, pristine pools of this liquid argon, cooled to cryogenic temperatures. Their strength lies in a remarkable property of the element itself. When a particle interacts in liquid argon, it produces not one, but two distinct signals that arrive at very different times. The first is a prompt flash of light emitted within nanoseconds of the interaction. The second is a much slower pulse of light caused by the decay of excited argon molecules, which takes microseconds to appear. The critical insight is this: the ratio of the fast light to the slow light is exquisitely sensitive to the type of particle that caused the event. An electron recoil, the signature of most common background radiation, produces a very different light ratio than a nuclear recoil, the hoped-for fingerprint of a dark matter particle. This powerful pulse-shaped discrimination allows argon-based detectors to sift through data with incredible precision, effectively separating potential signals from mundane noise right at the source. It is like having a built-in forensic lab that can instantly analyze the nature of every single interaction. This makes argon experiments exceptionally good at rejecting the radioactive backgrounds that are the bane of all dark matter searches. They provide a vital, independent check on the results from their xenon cousins. If the ghost is real and interacts as we suspect, it should leave its mark in both xenon and argon. A signal seen in one but not the other would be deeply puzzling, suggesting something far stranger is at play. So, the global hunt operates like a symphony with two lead instruments. The xenon experiments, with their massive targets and three-dimensional event mapping, listen with profound depth. The argon experiments, with their exquisite timing discrimination, listen with brilliant clarity. Their combined null result, this shared cosmic quiet, is a powerful chorus. It tells us that the simplest, most elegant version of the WIMP, the one theorists loved for decades, is fading from view. The ghost is not just hiding, it is playing by rules we have not yet fully deciphered. This growing tension is what now drives physicists to look beyond the mountain halls, to construct experiments of even greater audacity. But what if the ghost is not a heavy, lumbering giant, but something far lighter and more nimble? The silence from the massive liquid detectors whispers a hint, perhaps we are listening on the wrong frequency. This question led physicists to a different kind of trap, one made not of liquid but of frozen crystal, operating at the very edge of absolute zero. Deep in mines in Canada and the United States, experiments like SuperCDMS and EDELWEISS use ultra-pure germanium crystals as their ears. These are not cavernous vats, but exquisite, carefully sculpted ingots of semiconductor, cooled to temperatures within a few thousandths of a degree above absolute zero. At this frigid state, matter becomes almost perfectly still, and the crystals enter a quantum regime where they act as both target and sensor. The strategy here is to catch the faintest whisper of a vibration. When a particle, even a very light one, strikes an atom in the crystal lattice, it creates a minuscule shudder, a quantum of sound called a phonon. In these cryogenic crystals, that tiny packet of vibrational energy is enough to raise the temperature of the crystal by an almost imperceptible amount. Exquisitely sensitive thermometers bonded to the crystal can measure this infinitesimal pulse of heat. Simultaneously, the same particle interaction can knock electrons loose within the germanium, producing a small electrical charge. By measuring both the phonon signal and the charge signal from a single event, these experiments achieve a powerful discrimination, similar to the xenon and argon techniques, but optimized for an entirely different quarry. This dual readout technology makes germanium detectors phenomenally sensitive to low-mass dark matter candidates, particles that would be too light to leave a noticeable mark in the heavier xenon or argon nuclei. They are the delicate seismographs of the particle world, designed to feel the gentle footsteps of a much smaller ghost. While the ton-scale liquid experiments rule out vast territories for heavy WIMP, the germanium crystals are meticulously charting the landscape for lighter ones, probing a region of theoretical space that was once thought to be the most natural and elegant. Their ongoing silence, however, is just as profound. Even in these exquisitely tuned crystals, cooled to within a whisper of the coldest possible temperature in the universe, the expected signal has not appeared. Each experiment, whether it listens with liquid or crystal, is painting a more detailed picture of an absence. They are not finding nothing, they are discovering the precise shape of the mystery, defining the boundaries of where the ghost is not. This collective effort is a masterpiece of scientific deduction, a process of elimination on a cosmic scale, forcing us to ask with greater urgency, if the ghost is not here and not there, then where in the universe could it be hiding? While heavy particles and delicate crystals listen for a nuclear bump, another idea whispers from a completely different corner of physics. This candidate is not a WIMP, but a ghost of a different nature, born from a problem of exquisite symmetry in the heart of the atom itself. It is called the Axion, and its story begins not with missing gravity, but with a mysterious absence of imbalance. Within the realm of the strong nuclear force, the glue that binds protons and neutrons, physicists discovered a puzzle. The equations allowed for a certain kind of asymmetry, a parameter that should make particles and their mirror images behave very differently. Yet, in countless experiments, this asymmetry has never been observed. The universe appears perfectly symmetric in this specific, delicate way. To explain this puzzling perfection, theorists proposed a new field, and with it, a new particle. The Axion would be the whisper of that field, an ultra-lightweight particle billions of times less massive than even an electron, drifting through space in vast, cold waves. Crucially, this theoretical fix for a nuclear conundrum also produced a particle with the perfect properties to be dark matter. It would be neutral, stable, and produced copiously in the hot dawn of the universe, potentially accounting for every bit of the invisible mass we seek. The hunt for this wisp of a particle requires a radically different kind of trap, one that does not wait for a collision but for a transformation. This is the haloscope. The principle is a beautiful piece of quantum alchemy. In the presence of a strong magnetic field, an action should have a tiny chance to convert into a very low-energy photon, a microwave. Think of the magnetic field as a catalyst, a quiet stage that encourages the ghost to briefly manifest as a faint, specific note of light. The haloscope is essentially an ultra-sensitive microwave radio receiver, tuned to listen for that one note. The most famous of these is the Axion dark matter experiment, or ADMX. At its heart is a powerful superconducting magnet, colder than the void of space, generating an immense, steady magnetic field. Inside this field sits a resonant cavity, a carefully crafted metal chamber that acts like a tuning fork for microwaves. As the Axion waves wash through Earth, they permeate this chamber. If an Axion's mass corresponds to the cavity's precise resonant frequency, the conversion is amplified, producing a detectable whisper of microwave power. The challenge is staggering. The predicted signal is unimaginably faint, and the possible mass of the Axion is unknown. ADMX operates like the most patient radio dial in existence, slowly tuning its cavity through millions of distinct frequencies, listening intently at each one for a signal that rises just above the fundamental noise of the universe. It is a search for a single, quiet chime in a cosmic cacophony, where the musician and the note are both complete mysteries. This meticulous scanning represents a monumental engineering feat, pushing the boundaries of low-noise amplification and quantum measurement. While the massive liquid detectors listen for a knock in the dark, the haloscope listens for a ghostly hum, a conversion in the heart of a magnet. Its ongoing silence, like the others, is a profound data point, systematically ruling out entire ranges where this particular spectral ghost could be hiding. The patient scanning of a single resonant cavity, while powerful, faces a fundamental challenge of time. If the Axion's mass is not precisely aligned with the cavity's tuned frequency, its whisper goes unheard. To hunt this ghost more efficiently, physicists are now building new instruments that listen to many frequencies at once. or that force the action to reveal itself more boldly. This is the frontier of broadband and dielectric action searches, a next-generation quest to hear the universe's faintest hum. One ambitious approach abandons the single tuning fork model entirely. Experiments like HAYSTAC, the haloscope at Yale sensitive to action cold dark matter, operate on a broadband principle. Instead of one cavity painstakingly tuned across millions of frequencies, they use a system that can effectively listen to a small band of frequencies simultaneously. They achieve this through a technique called quantum squeezing, a way to manipulate the fundamental quantum noise that limits all such measurements. By squeezing this noise, they can reduce uncertainty in one aspect of the signal at the expense of another, effectively allowing their detector to be more sensitive across a range of frequencies at once. Think of it as adjusting a sophisticated microphone not just to be very sensitive, but to be sensitive in a particular way that filters out a specific type of static, making the faint notes you are searching for slightly easier to pick out across a chord rather than one note at a time. This allows HAYSTAC and similar experiments to scan through possible action masses significantly faster than traditional cavity haloscopes, covering more of the unknown territory where this lightweight ghost might be hiding. Yet another, even more audacious design seeks not just to listen but to shout back at the dark. This is the philosophy behind MADMAX, the magnetized disk and mirror action experiment. Its goal is to boost the action's conversion signal from a whisper to a shout. Instead of a hollow cavity, MADMAX plans to use a stack of many finely engineered dielectric disks, like a pile of extremely precise ceramic plates placed in a powerful magnetic field. Each disk acts as a boundary where the action-to-photon conversion can happen. The magic lies in the spacing. If the gaps between these disks are carefully calibrated to match the wavelength of the photon that a specific action mass would produce, the tiny conversion signals from each disk can be made to constructively interfere. Much like how the synchronized clapping of a large crowd creates a thunderous roar, the synchronized photon emissions from each disk would combine into a detectable flash of microwave light. This resonant enhancement could make the signal billions of times stronger than in a simple cavity. MADMAX represents a monumental engineering challenge, requiring the creation of nearly perfect, massive dielectric mirrors and moving them with microscopic precision inside a powerful magnet, all while cooled to cryogenic temperatures. But if it works, it will open a window to a higher range of action masses, exploring a region of possibility that has been completely inaccessible until now. Together, these advanced strategies form a pincer movement on the theoretical landscape. The broadband searches cast a wider, faster net, while the dielectric boosters aim to dredge the depths with unprecedented force. They are born from the same realization that guides the entire hunt. The ghost will not reveal itself easily. We must build ever more clever, more patient, and more forceful ways to ask our questions of the silent dark. If the ghost will not come to us, perhaps we can summon it into existence. This is the daring logic of the particle collider, a machine that does not listen or wait, but instead unleashes titanic forces to break reality apart and see what emerges from the wreckage. At the Large Hadron Collider beneath the border of France and Switzerland, protons are whipped to within a whisper of the speed of light and smashed together head-on. In these fleeting, microscopic fireballs, temperatures soar to levels not seen since the first instance of the Big Bang itself. The goal is to create conditions so extreme that they give birth to particles not seen in our ordinary, cold universe, including, we hope, the very particles of dark matter. But there is an inherent paradox in this plan. If dark matter interacts so weakly that it passes through our planet unseen, how could we possibly detect something created in a collision? The answer lies not in seeing the ghost, but in seeing the hole it leaves behind. Physicists search for an event with a profound imbalance, a case of missing momentum. In every proton collision, the total energy and momentum going in must equal the total coming out, a sacred law of physics. The debris from these explosions, a spray of familiar particles like quarks and electrons, is captured with immense precision by giant detectors like ATLAS and CMS. These are cathedral-sized instruments wrapped around the collision points, layered with sensors to track and identify every fragment. The computers reconstruct each event, calculating the paths and energies of all the outgoing particles. And sometimes they find a puzzle. The visible particles do not all balance each other out. There is a significant amount of momentum that seems to have simply vanished, shooting off perpendicular to the beamline, invisible to all sensors. This missing transverse energy is the signature of the ghost. It is the telltale sign that something was created in the collision that then fled the scene without a trace, carrying its momentum away with it. That something could be a dark matter particle streaming effortlessly through the miles of steel and concrete surrounding the detector, just as it streams through planets and stars. The ATLAS and CMS collaborations have dedicated teams sifting through billions of these collisions, searching for an excess of events with this specific kind of quiet emptiness, a statistical bump in the data that cannot be explained by any known process. They are looking for the shadow of a shadow, the empty space in the data where the ghost departed. So far, like the direct detection experiments, they have found no definitive signal. But this absence is a powerful cross-check. It tells us that if dark matter is a particle born in such collisions, it must be either too heavy for the collider to produce, or its connection to ordinary matter is even more tenuous than our best models predict. The collider does not wait for the universe to send us a ghost. It tries to manufacture one in a controlled blast of energy. Its continued silence, echoing the quiet from deep underground, is narrowing the path the ghost can take, forcing us to consider that its hiding place may be stranger and more subtle than our most powerful machines can yet probe. Yet the silence from our deepest minds and mightiest colliders is not the final word. The ghost may hide from our direct gaze, but it could betray itself through a final, violent act in the void of space. This strategy turns from listening for a whisper to searching for a flash of light from a distant funeral. The idea is called indirect detection, and it rests on a dramatic possibility. What if dark matter particles are not completely stable? Or what if they can occasionally find and annihilate one another? In either case, these events would transform the invisible stuff of the ghost into a burst of familiar, detectable particles, the most telling of which could be gamma rays, the universe's most energetic light. It is a search for the ghost shadow, not by its presence but by the luminous echo of its disappearance. The logic is compelling. We believe dark matter clusters most densely in the hearts of galaxies and in the faint, ancient dwarf galaxies that orbit our own. In these regions, the particles should be packed together far more tightly, increasing the chances that two might interact. If they annihilate or decay, the laws of physics dictate they must produce something we can see, often a cascade that ends with gamma-ray photons. Our tool for this cosmic forensics is the Fermi Gamma Ray Space Telescope, orbiting Earth with its Large Area Telescope, or LAT, constantly scanning the sky. It does not see the colorful cosmos of stars and nebulae. It sees a map of the most violent and energetic processes in the universe, the aftermath of supernova, the jets of black holes, and the fury of pulsars. Researchers using Fermi point this instrument at the most promising graveyards. The center of our own Milky Way is a prime target, a place where theoretical models suggest dark matter should be extraordinarily dense. And here, a tantalizing puzzle emerged. Fermi data revealed a faint, diffuse excess of gamma rays emanating from the galactic center, a glow that is difficult to explain with known astrophysical sources like pulsars or cosmic ray interactions alone. For a time, this galactic center excess sparked intense excitement, as its characteristics loosely matched predictions for certain types of dark matter annihilation. It was a ghostly glow in precisely the right place. But the universe is a messy place, and extraordinary claims require extraordinary evidence. The same dense region is also crowded with other, more mundane sources of gamma rays, including a population of thousands of unresolved pulsars. Distinguishing a smooth, dark matter halo glow from the combined flicker of countless faint but ordinary points of light is a monumental statistical challenge. The debate continues, with careful reanalyses of the data chipping away at the dark matter interpretation, suggesting the excess may yet be explained by conventional, if complex, astrophysics. This is why scientists have turned to cleaner, quieter cosmic laboratories, the dwarf spheroidal galaxies. These are small, faint satellites of the Milky Way, galaxies so dim they were discovered only by tracking the motions of their individual stars. They are held together by gravity, but they contain very few stars and almost no gas. What they do possess in abundance according to our models is dark matter. They are essentially pristine clumps of the ghost, with very little of the messy astrophysical background that complicates the view of our galactic center. Fermi has spent years staring at these quiet dwarfs, collecting every precious gamma-ray photon. The result, once again, is a profound quiet. No significant, unexplained gamma-ray excess has been found from any of them. This non-detection is a powerful constraint. It tells us that if dark matter particles do annihilate or decay, they must do so at a rate far slower than many popular theories predicted. The ghost, it seems, is not only shy in life, but remarkably discreet in death. The search for its final flash of light continues, but the deepening silence is guiding theorists toward models where the ghost is even more isolated, more sterile, and more stubbornly hidden than we ever imagined. High above the Earth, a different kind of detective sifts through the debris of the cosmos. Attached to the International Space Station, the Alpha Magnetic Spectrometer, or MS-02, is not a telescope but a precision cosmic ray analyzer. It faces the hard vacuum of space, its powerful magnet and layers of sensors designed to perform a daunting task: identify and count the subatomic shrapnel that constantly rains down on our planet. Among this hail of particles are rare and precious clues: antimatter. For every familiar particle like the electron or proton, there exists an antimatter twin with opposite charge. When matter and antimatter meet, they annihilate in a flash of pure energy. In the calm of today's universe, antimatter is extraordinarily rare, making its presence in cosmic rays a potential fingerprint of something dramatic. This is where the ghost enters the story. If dark matter particles are annihilating in the Milky Way's halo, as indirect detection hopes, those collisions should produce showers of standard particles, including antimatter-like positrons, the antimatter twins of electrons, and antiprotons. These antimatter particles, born from the ghost's demise, would then get caught up in the galactic magnetic fields, spiraling for millions of years before some eventually wander into our detectors. Experiments like MS-02 and its predecessor, Pamela, have been meticulously counting these rare arrivals, and they found something intriguing: an excess. The number of high-energy positrons detected is significantly higher than what standard models of cosmic ray propagation predict. The data shows a smooth rise in the positron fraction that cannot be easily explained by known astrophysical processes alone. For a moment, it seemed like the ghost's funeral pyre might have been glimpsed. The signature was tantalizing, a whisper of antimatter from the dark. But the cosmos rarely offers simple answers. A compelling alternative explanation emerged from the very objects that light up the gamma-ray sky: pulsars. These rapidly spinning neutron stars are natural particle accelerators of immense power, capable of generating intense winds of electrons and positrons. As these particles travel through space and interact with interstellar gas and light, they too can produce an excess of positrons that would wash over our solar system. Distinguishing between the two origins, a smooth, diffuse dark matter halo versus the combined output of numerous pulsars, is a monumental forensic challenge. The debate is a beautiful example of scientific rigor at work. Proponents of the dark matter interpretation point to the smoothness of the observed positron spectrum, which might better fit a widespread source like annihilating dark matter. Others build increasingly sophisticated models showing how populations of known pulsars could collectively produce the signal. AMS-02 continues to gather data, its precision improving with each passing year, adding more statistics to this cosmic jury. The ongoing ambiguity itself is a profound result. It tells us that the ghost, if it is annihilating, is doing so at a rate so subtle that its signal blends almost perfectly with the spectacular astrophysical background of our own galaxy. The antimatter excess remains a clue written in vanishingly faint ink, a mystery that pushes our understanding of both dark matter and the complex astrophysics of our own cosmic neighborhood to their very limits. Deep within the polar ice, another kind of telescope points not at the sky but straight down through our planet. The ghost, if it is hiding in the heart of our sun, could be sending us messages written in the most elusive script in the universe. This is the realm of neutrino astronomy, and it offers a third path for indirect detection, one with a startlingly clear return address. Neutrinos are the universe's ultimate ghosts, even more ethereal than our dark matter quarry. Trillions pass through your thumb every second, born from nuclear fires in stars and cataclysmic cosmic events, interacting with matter so rarely they are almost a myth. To catch them requires detectors of monumental scale and patience. Enter IceCube at the South Pole, a cubic kilometer of pristine glacial ice instrumented with over 5,000 light sensors, and SuperCDMS, and in Japan, a cavern filled with 50,000 tons of ultra-pure water. These are neutrino telescopes. They watch for the rare, telltale flash of blue light, called Cherenkov radiation, produced when a neutrino finally does interact with an atom in the water or ice, creating a fleeting charged particle that moves faster than light can travel in that medium. It is like catching the shadow of a shadow. But what does this have to do with dark matter? The connection is a beautiful chain of cosmic logic. As the sun moves through the galactic halo, it should also be sweeping up dark matter particles. If those particles interact even very weakly with ordinary matter, a small fraction could be slowed and gravitationally captured, sinking over eons into the sun's dense core. There, in that immense pressure cooker, the concentration of dark matter could become high enough that particles find and annihilate each other. The energy from that annihilation would produce a cascade of standard particles, and among them would be a burst of high-energy neutrinos. These neutrinos, born in the solar core, would then race out in all directions, and here is the brilliant signature. Unlike gamma rays or charged particles, which get scattered and redirected by magnetic fields, neutrinos travel in perfectly straight lines, unaffected by almost everything in the cosmos. A neutrino detected from the direction of the sun carries with it an unambiguous label, made in the core. So, experiments like IceCube and SuperCDMS and point their vast volumes toward our star, filtering through countless other neutrino signals from across the cosmos, searching for an excess of high-energy neutrinos with that precise solar origin. They are looking for the faint, straight-line telegram sent from the ghost's gathering place inside our own star. The signal would be a smoking gun, a directional clue so clear it would be incredibly difficult to explain by any other astrophysical process. Yet once more the result is a profound quiet. The sun, in neutrino light, appears normal. No extraordinary flux of high-energy neutrinos has been found streaming from its center. This non-detection is another powerful constraint, telling us that if dark matter is being captured by the sun, its annihilation rate is vanishingly small, or perhaps it does not annihilate in this way at all. The silence from the ice and the water is a message written in straight lines from the heart of our nearest star, and it whispers that the ghost's preferred method of disappearance is even more secretive than we dared to suppose. Beneath a mountain in Italy, a detector has been whispering the same secret for over 20 years. The DAMA/LIBRA experiment is the ghost hunter's oldest and most persistent puzzle. While other experiments report only silence, this one records a faint, rhythmic pulse. Its event rate rises and falls with the precise regularity of a cosmic metronome, ticking once every Earth year. The team's interpretation is a compelling story written in our planet's motion. As we orbit the Sun, our entire solar system is sailing through the Milky Way's vast, still ocean of dark matter. In June, Earth moves headlong into this cosmic current. In December, we move with it. The theory predicts that this should create an annual modulation in the rate at which dark matter particles stream through our detectors. A higher wind in our face in summer, a lower one at our back in winter. DAMA/LIBRA claims to have measured exactly that, a gentle seasonal sway in its data that matches the predicted pattern for a dark matter wind. It is a signal of elegant simplicity, one that has persisted through multiple upgrades of the experiment itself, growing stronger with accumulated data. This is not a fleeting blip, it is a 2-decade-long hum from the deep, yet this hum exists in profound isolation. No other major dark matter experiment, using different target materials and techniques, has been able to confirm it. This discrepancy has sparked one of the most intense and meticulous scientific debates of our time. The entire field has mobilized to solve the DAMA riddle. Rival collaborations have built experiments designed specifically to test the signal under nearly identical conditions. They use the same target material, sodium iodide crystals, and operate in the same deep underground laboratory. They have sought to replicate every possible detail, listening for the same modulation in the same quiet mountain hall. So far, these dedicated checks have heard nothing out of the ordinary. The original signal stands alone, an unconfirmed siren song. This has led to a parallel, exhaustive effort to find a mundane explanation, to prove the hum is an echo of something else. Could it be a subtle seasonal effect? Changes in underground temperature, humidity, or even the composition of the rock itself over the year. Perhaps it is linked to cosmic rays, whose flux might also modulate slightly with Earth's orbit. Teams of researchers have combed through every conceivable environmental variable, modeling and testing with obsessive precision. To date, no conventional cause has been found that can fully account for the strength and clean periodicity of the DAMA modulation. The result is a perfect scientific stalemate. One side points to a signal that beautifully matches a key dark matter prediction. The other points to the unanimous silence from every other listening post on the planet. It is a conflict not of personalities but of data, and it forces a humbling admission. We do not yet know if DAMA has glimpsed the ghost, or if it has discovered a new, utterly unexpected form of background noise that teaches us something profound about our own planet. This unresolved anomaly is a testament to the complexity of the hunt. It reminds us that the universe's quietest signals lie on the knife's edge between revolutionary discovery and deeply hidden error. Until another experiment finally hears the same rhythm, or definitively traces it to an ordinary source, this 20-year whisper from beneath Gran Sasso will remain one of the most tantalizing and frustrating clues in the search for what holds our universe together. The persistent quiet from conventional detectors is not a wall, but an invitation to invent new ways of listening. This frontier is built not on tons of liquid or crystal, but on the bizarre rules of the quantum world, where observation itself becomes the most delicate tool. Here, physicists are designing sensors so sensitive they could register the gentle pressure of a single quantum of sound, or the faintest tickle of a magnetic field, hoping to feel the passage of a ghost 1 billion times lighter than any WIMP. One of the most ethereal approaches uses superfluid helium. When cooled to near absolute zero, helium loses all viscosity and friction, becoming a perfect quantum fluid. In this state, it can support exotic vibrations called quantum vortices and phonons with almost no energy loss. Experiments like Herald and Alethea propose using superfluid helium as both target and sensor. The idea is that an incoming dark matter particle, even an incredibly light one, could deposit a minuscule amount of energy into the superfluid, creating a tiny cascade of excitations, rotating vortices and quantized waves of sound. By using grids of superconducting wires to detect the minute electrical currents induced by these vortices, or by measuring the faint photons emitted when the excitations recombine, scientists hope to sense interactions far too gentle to budge a heavy atomic nucleus. It is like trying to detect the ripple from a single raindrop falling into a perfectly still, frictionless ocean. Another quantum strategy abandons bulk materials entirely, aiming to use single, isolated atoms or electrons as the target. This is the realm of quantum dots and single electron transistors. Imagine confining a single electron in a tiny semiconductor trap, a quantum dot, and holding it in a precise, fragile quantum state. The passage of a dark matter particle could impart a minuscule kick to this electron, perturbing its quantum state in a detectable way. Because the target is a single, fundamental particle, not a massive nucleus, the sensor becomes exquisitely sensitive to very low mass candidates that would simply brush past a larger atom. It is the difference between trying to hear a whisper by listening to a vibrating cathedral bell versus listening to the tremor of a single, suspended guitar string. The most mind-bending proposals venture into optomechanics, where light and motion become entangled. Here, scientists engineer microscopic, mirror-like membranes or vibrating nanowires, cooled to their quantum ground state, the point of minimum possible vibration. In this ultra-quiet condition, even the quantum jitter of the atoms is suppressed. A hypothetical dark matter particle interacting with this device could give it a barely perceptible push, a displacement smaller than the diameter of a proton. By shining laser light on these nanoscale objects and measuring with phenomenal precision how their vibration frequencies or positions change, researchers hope to see the ghost's gentle nudge. These are not just new experiments, they are new senses. They represent a fundamental shift in strategy, acknowledging that if the ghost is ultra-light and fleet, we must stop trying to hear its footsteps and instead learn to feel its breath. Each of these quantum devices is a leap into the unknown, pushing measurement science to its absolute limits, all to explore a vast, uncharted territory of possibility where the ghost, in its lightest form, might finally leave a trace we can comprehend. Perhaps the ghost is not a particle at all, but a vast, shifting texture in the fabric of reality itself. This idea pushes beyond the search for individual specks of dark matter, proposing instead that it could form immense, coherent structures, cosmic wrinkles or walls that sweep through the galaxy, bending the rules of physics as they pass. To hunt for these ephemeral giants, scientists have built a different kind of detector, one that spans the entire globe. The Global Network of Optical Magnetometers for Exotic Physics, or GNOME, is a web of synchronized sensors on nearly every continent. Each station is a highly sensitive optical magnetometer, a device that can detect the most minuscule changes in a local magnetic field. The network's quarry is a hypothetical structure called a domain wall. Think of it as a boundary between two different phases of the dark matter field, a sheet of energy thinner than an atom but stretching for millions of kilometers across interstellar space. As Earth orbits through the galaxy, it could occasionally pass through such a wall. The theory suggests that as this wall sweeps through a GNOME sensor, it would momentarily and very slightly alter the fundamental constants of nature, like the mass of an electron or the strength of the magnetic force. This tiny shift would register as a synchronized blip in the magnetic readings across multiple stations, a coordinated whisper from sensors thousands of miles apart. By looking for these globally correlated signals in real time, GNOME transforms our planet into a single, planet-sized antenna, listening not for a particle's bump, but for the gentle pressure of a cosmic curtain brushing past our world. It is a search for dark matter as a macroscopic field, a ghost not of substance but of structure. If dark matter can form such immense structures, could it also gather into dense, swirling clouds that literally bend space and time? This question leads us to the most sensitive rulers ever constructed, the gravitational wave observatories. The Laser Interferometer Gravitational Wave Observatory, or LIGO, along with its partners Virgo in Italy and Kagra in Japan, have opened an entirely new window on the universe by detecting ripples in spacetime from colliding black holes and neutron stars. But their exquisite sensitivity might also tune into the ghost in a different way. One provocative idea suggests that vast clouds of ultra-light dark matter particles, potentially the actions we discussed earlier, could condense around black holes, forming swirling, wave-like halos. These boson clouds, as they are called, would not be silent. As they rotate and interact with the black hole's immense gravity, they would themselves generate a continuous, faint hum of gravitational waves, a monotone note in the cosmic symphony. LIGO and Virgo, constantly listening to the universe's gravitational soundtrack, could potentially pick up this persistent background hum from such clouds in our galaxy. Even more strikingly, if a dense clump or soliton of dark matter were to pass near Earth, its gravitational pull could minutely distort the precisely measured lengths of the interferometer's laser arms, creating a distinctive signal. It would be a direct tug on the fabric of spacetime itself, a signature written not in light or particles but in geometry. The LVK collaboration, the collective name for LIGO, Virgo, and Kagra, actively sifts through its data for these exotic possibilities. They are listening for the ghost's mass warping the stage of reality, a tremor so subtle it requires lasers traveling down 4-kilometer vacuum tubes to sense a displacement 10,000 times smaller than a proton. This approach reimagines dark matter not as something we might see or touch, but as a dynamic feature of the cosmos that plays the instrument of spacetime. Each non-detection from this global network of magnetometers and interferometers is another careful stroke, painting the ghost not as a point, but as a landscape we are only beginning to map. The most ancient light in the universe carries a memory of the ghost. This is the cosmic microwave background, a faint afterglow that has been traveling for over 13 billion years, since the cosmos was a mere infant, hot and dense, and just 380,000 years old. When we point our telescopes at this primordial glow, we are not just looking at a snapshot of the infant universe, we are reading a detailed birth certificate for everything within it, including dark matter. The patterns woven into this light, tiny variations in temperature from one patch of sky to another, are frozen ripples from the universe's first moments. They are the seeds from which all cosmic structure grew, the gravitational wells that would one day pull together to form galaxies and clusters, and the way those patterns look tells a precise story about what was in the mix. Imagine trying to understand the ingredients of a cake by studying the precise texture of its crumb. The CMB is that cosmic crumb. Missions like the European Space Agency's Planck satellite have mapped these temperature variations with breathtaking precision, creating a sky map of incredible detail. The size and distribution of these hot and cold spots are not random. They follow a specific statistical pattern that acts as a cosmic ledger, recording the relative amounts of ordinary matter, dark matter, and dark energy in the early universe. The ledger is clear and unequivocal. To create the exact pattern of spots we see, the universe required about 5 times more matter than what is present in all the atoms of stars, gas, and planets. This invisible majority had to be cold, meaning its particles were moving slowly in that early epoch. If dark matter had been hot or fast-moving, it would have smoothed out those tiny infant ripples, preventing them from growing into the grand cosmic web we see today. The CMB tells us the ghost was not only present at creation, it was the dominant architect sitting quietly in the gravitational driver's seat from the very beginning. This is perhaps the most powerful dark matter experiment of all, one conducted by the universe itself across billions of years. It gives us a number, a fundamental percentage etched into the oldest light there is, and it demands that any particle we propose must fit perfectly into that ancient, frozen picture. The ghost shadow is cast across the first dawn. These pristine cosmic laboratories are not found in the brilliant hearts of great galaxies, but in their quiet, dark shadows. Orbiting our Milky Way are dozens of faint, ancient dwarfs, galaxies so dim they were discovered not by their light, but by the motion of a few scattered stars within them. They are the galactic equivalents of a ghost town, holding a profound secret in their emptiness. Their power as a dark matter lab comes from a simple, telling ratio, mass to light. For a typical galaxy like our own, this ratio tells you how much total mass you have for every unit of starlight. The Milky Way's ratio is substantial, but the numbers for these dwarf spheroidals are staggering. They possess hundreds, sometimes thousands, of times more mass than their faint starlight can account for. This means they are not just sprinkled with dark matter, they are utterly dominated by it. They are essentially massive, fluffy clouds of the ghost, with just a few ancient stars sprinkled inside like accidental ornaments. This purity is what makes them such a critical testing ground. In the crowded core of our own galaxy, the signal from annihilating dark matter is muddied by pulsars, stellar remnants, and cosmic ray interactions. It is like trying to hear a single instrument in the roar of a symphony. But in the dwarf galaxies, the symphony is almost silent. The astrophysical background noise is minimal. If dark matter particles annihilate anywhere and produce gamma rays, the cleanest, strongest signal should come from these dark, quiet halos. For over a decade, the Fermi Gamma Ray Space Telescope has stared at these dwarfs, collecting every precious photon. The result has been a powerful, deepening quiet, ruling out many popular models of annihilating dark matter. But the hunt is about to gain a revolutionary new sense. The upcoming Cherenkov Telescope Array, or CTA, represents a quantum leap. Unlike Fermi, which detects gamma rays directly in space, CTA will be a ground-based array of over 100 telescopes spread across 2 hemispheres. It will not catch the gamma rays themselves, but the fleeting flashes of blue Cherenkov light they create when they strike Earth's atmosphere. This technique allows CTA to see the most energetic gamma rays with unprecedented sensitivity and resolution. When it turns its collective eye toward a dwarf galaxy, it will not just see if there is a glow, it will potentially map the structure of that glow, testing whether it matches the predicted shape of a smooth dark matter halo versus the clumpy output of any remaining conventional sources. It is the difference between hearing a faint note and being able to identify the exact instrument that played it. The continued silence from these pristine dwarfs would be a message of profound importance, telling us the ghost is even more isolated and sterile in its interactions than our most conservative theories allow. A clear signal, however, would be a beacon from the dark, a fingerprint of annihilation from the quietest places we know, offering our clearest glimpse yet into the ghost's hidden nature. One of the most persistent and natural questions arises from all this searching. Could the ghost simply be made of ordinary stuff, just hidden in plain sight? This idea seems beautifully simple, Perhaps dark matter is just vast clouds of cold hydrogen gas, or swarms of dim, failed stars, or ancient black holes littering the galactic halo. These are known as MACHO, massive compact halo objects, made of baryonic matter, the same protons and neutrons that build you and me and every star. For a time, this was a compelling alternative, a way to solve the mystery without inventing new physics. But the universe itself has conducted two definitive experiments that together close this door. The first experiment happened in the universe's first 20 minutes. In that fiery dawn, the cosmos was a nuclear fusion reactor, forging the lightest elements, hydrogen, helium, and a trace of lithium. This process, Big Bang nucleosynthesis, is a precise cosmic recipe. The amounts of each element produced depend critically on one thing: the density of baryons, the ordinary matter particles in the early universe. Too many baryons and nearly all the hydrogen would have fused into helium. Too few and almost no helium would exist. We can observe the primordial abundances of these elements in the oldest stars and in distant, pristine gas clouds. The observed ratios match the predictions of nucleosynthesis perfectly, but only if the total amount of baryonic matter in the cosmos is strictly limited. That measured amount accounts for all the stars, galaxies, and gas we see, plus a little more. Crucially, it is only about 1/5 of the total matter we know must exist from gravitational measurements. The universe's own cookbook tells us there simply is not enough ordinary ingredient to make up the ghost. 5 times more matter is needed than the recipe allows for. This leaves the possibility of dark, compact baryonic objects, the MACHO. Could the halo be filled with planet-sized lumps or stellar mass black holes that emit no light? To test this, astronomers performed a clever celestial survey. They used gravitational microlensing, a small-scale cousin of the lensing that bends galaxy light. The idea was to stare at millions of stars in a neighboring galaxy, the Large Magellanic Cloud. If a massive, invisible object like a black hole drifted through the halo and passed directly in front of one of those distant stars, its gravity would act as a tiny lens. For a few days or weeks, it would magnify the star's light, causing a characteristic brightening and fading. Dedicated projects like the MACHO and EROS collaborations monitored these stars for years. They saw a handful of microlensing events, but far, far fewer than would be required if such objects made up the bulk of the dark matter halo. The verdict was clear. While some MACHO undoubtedly exist, they are a tiny population. They cannot be the dominant form of the missing mass. Together, these two independent probes, one from the universe's first moments and one from patient stellar observation, form an airtight case. The ghost is not hidden baryonic matter. It is not gas, dust, dim stars, or stray black holes. It is something else entirely, a substance that does not participate in the nuclear reactions that lit the early cosmos, and does not reveal itself in the subtle brightening of distant suns. This conclusion is what makes the search so profound. We are not looking for a hidden version of ourselves. We are hunting for a fundamental component of reality that operates outside the rules of our familiar world. This relentless silence from every frontier is not a failure of imagination, but a message of profound clarity. The ghost is telling us with increasing insistence that it does not live where we first thought to look. To understand this, we must visualize the entire territory of possibility, a map scientists call the parameter space. Picture a vast, blank sheet of paper stretching to the horizon in 2 directions. One axis represents the possible mass of a dark matter particle, from the weightless whisper of an action to the mountain-like mass of a black hole seed. The other axis represents its interaction strength, how likely it is to bump into the ordinary matter of our detectors, from utterly ghostly to almost tangible. Every single model for a dark matter particle, every theory from WIMP to Actions, occupies a specific point on this immense map. For decades, our experiments have been explorers, venturing into this unknown landscape with torches of increasing brightness, illuminating one region after another. The massive liquid xenon detectors have scoured the territory of heavy particles with moderate interaction strength, ruling out entire mountain ranges of possibility. The cryogenic crystals have swept through the valleys of lighter masses. The haloscopes have meticulously scanned the planes of the ultralight action. The colliders have probed the high-energy frontiers, and with each new, more sensitive experiment, the illuminated area on the map grows larger, revealing more of the blank territory where nothing has been found. The stunning result, after all this effort, is that the map remains overwhelmingly empty. The simple, elegant regions we thought most likely to harbor the ghost have been thoroughly searched and found vacant. This is the parameter space problem. We have not simply failed to find dark matter, we have successfully discovered where it is not, and that discovery is forcing a monumental shift. The comfortable, well-motivated spots on the map are now behind us. To continue the hunt, theorists must now propose particles that live in the remaining, far more exotic corners, places where the interaction is so infinitesimally weak, or the particles so bizarrely configured that our current generation of traps simply cannot sense them. The ghost is not absent, it is receding into a wilderness of theoretical possibility, a landscape where the rules themselves may be different. This narrowing path is the first great reason for its enduring secrecy. Our very success at exploration has defined the scale of the mystery, revealing that the answer lies not in refining our current tools, but in perhaps inventing entirely new ways to see. For decades, one elegant idea held a near-hypnotic sway over the entire search. It was known as the WIMP miracle, and it felt less like a theory and more like a cosmic wink. The miracle was this stunning numerical coincidence. Physicists calculated that if a particle existed with a mass around 100 times that of a proton and interacted only through the weak nuclear force, something extraordinary would have happened in the fiery first moments of the Big Bang. As the universe expanded and cooled, these particles would have frozen out of the primordial soup at precisely the right abundance to account for the dark matter we observe today. The numbers aligned with breathtaking precision, as if the universe had solved its own missing mass problem with a single, beautiful equation. This was not just a candidate, it felt like a prediction. The WIMP was not merely possible, it was natural, even inevitable, tying together the physics of the very small with the fate of the very large. This elegant promise focused the field like a laser. It told experimentalists exactly where to look and what to build, channeling immense resources and brilliant minds into the direct detection experiments we have explored, the massive vats of xenon and argon deep underground. The WIMP was the star around which the entire dark matter solar system orbited, but miracles in science must ultimately face the data, and the data has delivered a long, unbroken silence. Year after year, experiment after experiment, the predicted signal has failed to appear. The parameter space where the miracle lived has been meticulously swept clean. This persistent null result has initiated a slow, profound, and necessary philosophical shift across the field. The luster of the WIMP miracle has undeniably faded. Its elegant coincidence now feels, to many, more like a beautiful dream, a siren song that led us deep into the wilderness but not to the treasure itself. The ghost, it seems, did not get the memo about being so conveniently tied to the weak force. This is not a story of failure, but of maturation. The field is undergoing a graceful broadening, a necessary diversification of strategy. The intense focus on the heavy WIMP has relaxed, making intellectual and financial space for the ultralight action, for hidden sector particles that interact only with themselves, for macroscopic blobs of strange matter, and for ideas we have not yet named. The experimental portfolio is now richer and more varied than ever before. We are no longer betting everything on a single, elegant hunch. We are exploring the map in all directions, acknowledging that the ghost's secrecy may be a sign not of our poor hearing, but of its truly alien nature. The end of the WIMP dominance is a liberation, opening the door to a universe that might be far stranger and far more interesting than even our most elegant miracles could predict. Perhaps the ghost is not a substance but a flaw in our most trusted law. This is the most radical question one can ask in this entire search. Could we be fundamentally wrong about gravity itself? For centuries, Newton's laws, refined by Einstein, have been the bedrock of our cosmic understanding. They predicted the orbits of planets, the bending of starlight, and the expansion of the universe. But what if, on the vast, lonely scales of galaxies, these laws subtly break down? What if dark matter is not a missing ingredient, but a sign that our recipe for gravity is incomplete? This idea leads to a family of theories known as modified Newtonian dynamics, or MOND. Its proposal is startlingly simple. Instead of invoking an invisible sea of particles, MOND suggests that gravity behaves differently when it becomes extremely weak, such as in the outer reaches of galaxies where stars feel only a faint pull. The theory introduces a new, very small acceleration scale. Above this scale, gravity works exactly as Newton and Einstein described, but below it, the force changes, becoming stronger than expected. This single tweak to the math can beautifully reproduce the flat rotation curves of spiral galaxies, the very observation that launched the dark matter hunt. Without a single invisible particle, MOND explains why stars on the galactic edges move so fast. It is an elegant Occam's razor, cutting away the need for an entire unseen universe. For its supporters, it is not a ghost we are chasing, but a mirage created by our own misunderstanding. The theory has even seen intriguing successes, predicting detailed aspects of galactic motion that the standard dark matter model sometimes struggles with, all without adjustable parameters. Yet for all its elegance on the scale of individual galaxies, MOND faces a universe of complications. Its greatest challenge comes from the cosmic stage where dark matter's evidence is overwhelming, the immense clusters of galaxies. When galaxies collide, like in the famous bullet cluster, observations show that most of the mass, mapped through gravitational lensing, is clearly separated from the visible stars and gas. This is interpreted as dark matter, which is collisionless, sailing ahead of the ordinary matter that slows down due to friction. MOND, in its basic form, struggles to explain this clean separation of mass from light without invoking some form of unseen matter, which would defeat its core premise. Furthermore, the detailed pattern of the cosmic microwave background, that ancient light from the infant universe, requires the precise amount and behavior of cold, dark matter to create the cosmic web we see. Reproducing this perfect snapshot with a modified gravity theory alone has proven extraordinarily difficult, though not impossible. Relativistic extensions of MOND, like TVS, have been crafted to fit within the framework of Einstein's spacetime, attempting to meet these cosmological challenges. They are intricate and mathematically complex, but they often must introduce new fields that, ironically, begin to resemble the very dark substances they sought to replace. The debate between modified gravity and dark matter is not a fringe argument. It is a rigorous, necessary tension at the heart of cosmology. It forces us to confront the bedrock of our knowledge. Do we trust the overwhelming, consistent evidence for an invisible substance from the CMB, to galaxy clusters, to gravitational lensing, and invent a new particle to explain it? Or do we take the galactic rotation curves as a clue that our theory of gravity, successful everywhere else, needs a fundamental revision on cosmic scales? The ghost, in its silence, keeps both possibilities alive. It reminds us that the greatest mysteries often point not just to what we do not know, but to what we assume we know for certain. This monumental search, spanning continents and decades, represents one of humanity's most ambitious scientific endeavors. We have built underground cathedrals of liquid xenon, tuned cryogenic crystals to hear quantum whispers, and transformed our planet into a network of synchronized magnetometers. We have pointed telescopes at the oldest light in the universe and at the quietest dwarf galaxies, while particle colliders try to summon ghosts from microscopic fire. Each of these 20 frontiers is a testament to our ingenuity, a marvel of technology designed to perceive the imperceptible. Yet here we stand, at the edge of a profound and beautiful irony. The evidence for dark matter's gravitational influence has grown only stronger, more undeniable with each passing year. From the spin of galaxies to the bending of light across the cosmic web, its shadow is cast across the universe. And yet, its direct identity, its fundamental nature, remains more elusive than ever. The ghost's presence is undeniable, but its substance retreats further into the dark with every experiment we build. This is not a story of failure. It is the precise signature of science working at its cutting edge. Every silent detector, every null result, is a powerful form of discovery. They are not empty answers, but precise measurements of the mystery's shape. Each one carves away a vast territory of what dark matter is not, guiding us with painstaking clarity toward what it might be. We are being led by the ghost itself, through its very silence, toward a truth that will likely revolutionize our understanding of the cosmos. The next generation of experiments is already taking shape, born from the lessons of this great quiet. They will be more sensitive, more clever, and more diverse, probing the wilderness of theoretical space we have only just begun to map. This journey reminds us that the universe's deepest secrets are not given up easily. They are earned through patience, through collective wonder, and through the courage to keep listening to the silence, knowing that within it may lie the whisper that changes everything.